So our second speaker is Hongbin Chen from New York University, who will talk today about atypical exit events near a repelling equilibrium.
Okay, thank you for the invitation. So let's see. Okay, first let me describe the setting. So we are in Euclidean space, and let D be a domain. We assume it contains the origin. Let dynamics be given by ODE, and we assume the ODE has repelling equilibrium at the origin, and that's the only equilibrium in this domain. Then we just consider um, a white noise perturbation of the ODE given by the SD, where epsilon is the noise magnitude. Then we consider the exit time, which is tau epsilon, just the first time for the process to get outside of D. We are interested in the exit distribution, that is the law of eps tau as epsilon goes to 0, and when the process starts near the equilibrium, that is starts near the origin. Okay, so this is setting, and so it is known that the typical exit happens along the most unstable direction. So let me just describe describe what is the most unstable direction. We assume the vector field has some linearization at the origin. Then the most unstable direction or the most unstable flow or the manifold is a flow generated by the eigenvector corresponding to the largest eigenvalue. Then we know that this green path is going to be a typical one, and the red one is going to be atypical because it does not exit at those two green points. So we want to know what the decay rate for those atypical events. Does any scaled limit exist? Then we want to know what's the asymptotics for exit distribution condition on those atypical exits. So this is a type of small perturbation of dynamic persistence, and it has been studied extensively, for example, in Fredlin and Wenzel theory. A particular picture in that framework is you have a stable equilibrium at the origin. So you have a strong contraction of vector fields. So it can be expected that atypical event is going to be decaying exponentially in epsilon as epsilon goes to 0. However, in our case, we have an unstable and in fact repelling equilibrium, and we are going to see atypical events in our case decay polynomially, and we are going to get exact asymptotics and scale the limits. So things are already interesting in the most simple case. Suppose we are now in 2D and we consider this, we just have a box, the domain is a box, and the dynamics are linear. You have epsilon and epsilon 2, lambda 1 larger than lambda 2, they are the eigenvalues. And those yellow two arrows corresponding to the unstable directions. Therefore, typical exits, we know that the exit distribution should concentrate on those two green points as epsilon goes to 0. Then we know that the exit from the top and the bottom edges is going to be atypical. So we want to ask what is the conditional distribution, conditional exiting from top and bottom edges. I mean, we know that typically it's going to be exiting through the most unstable direction. So it may be reasonable to guess that this is going to concentrate on the 4 corners, right? Because those 4 corners, if you just draw the parabolas for those flows, then those 4 corners, they are very close to the unstable direction. So maybe it's reasonable to say that it's concentrates on the four corners. However, this is not true. And in fact, in this linear case, it's going to be uniform on those 2 edges. So this is the a phenomenon of equidistribution, and this is a key feature in our scenario. Okay, so basically, it tells you that if the flow if the process does not actually at a typical location, then there's kind of equal chance to exit at any atypical locations. Yeah. Okay. So a general setting, the general setting we consider is in RD. We assume the vector field has linearization given by diagonal matrix with distinct eigenvalues, and they are ordered in this way. And let's MK, we can then define the unstable manifolds associated with these vectors eigenvalues. So MK is going to be the k-dimensional unstable manifold associated with the top k eigenvalues. So somehow you can view MK maybe just as the union of all flows passing through the origin, whose tangent at the origin belongs to the span of the first k eigenvectors. Okay, so now we have a sequence of unstable manifolds, and they are included in each other. Then for a set on the boundary of the domain, we can define an index is going to be the smallest integer such that A intersects MK is not empty. So the index of the set actually characterizes the decay rates of exiting from A. And for each index, we associate some decay exponents, which are given by rho 1 up and to rho d. They are given by this formula in terms of those eigenvalues lambda. Finally, we associate with each index a measure, which can be expressed explicitly, but it's not important here. We just need to know they are k-dimensional, k-1 dimensional house of measure on the boundary of the domain, and it's spotted on the intersection boundary with k manifold. So we have two theorems here. So eventually we have two theorems. If A is a set is regular enough on the boundary, and it has index I, then the probability of exit from A is going to be decaying like epsilon to the power rho I. The scaled limit is given by mu I. The second theorem is just we take a quotient and we have this convergence of the conditional law. Okay, so these are the main results we have. And somehow it is a little bit heavy on notation, so I'm going to illustrate the this phenomenon by example. So suppose now we are in 3D, and this is I think it's a unit ball, any like object. So suppose M1 is a one-dimensional manifold given by this green curve, and M2 is a disk-like surface, and M3 is an infinite ball. And here we have three sets, A1, A2, A3. They are sitting on the boundary of the ball. That is, they are sitting on the sphere, or sphere, sphere-like boundary. So recall the definition of the index is the minimum case such that A intersects MK is not empty. So since A1 intersects M1, the index of A1 is 1, A2 does not intersect the M1, but intersects M2, so its index is 2, and A3, its index is 3. Yeah. Then theorem 1 tells you, gives us the scaled limit of this exit event, and then we can kind of compute or just see the like rough asymptotics of these probabilities. So A1, it's a typical location for exit. So the probability is going to converge to a constant. For A2, we know that it is atypical and the decay rate is given by rho2. So it is scaled like epsilon to the power rho2. And the measure mu2 here is one-dimensional, supported on the intersection with M2. So it's roughly the length of this red curve, which is intersection of A2 with M2. And for A3, you know this decay rate, and mu3 here is a two-dimensional measure. It's actually supported on the entire boundary. So you have, it's roughly this scaling times the area of A3. Yep. So this just this is an example illustrating the results. And let me briefly discuss the proof. So, so for the most general case, it is very hard to do computations. So what we do first is we just compute asymptotics of exiting a box in the linear dynamic, um, in the case of linear dynamics. So it is still a little bit uh, not too easy because the diffusion term, we assume it to be multiplicative, not additive. So even though in the linear case, we can express the solution as this using two-Helmholtz formula, here U is a Gaussian-like process. It's not actually Gaussian. And in the end, we realized that we actually need to bound the give a density estimate. So here we bound the difference between the density of UT and MT by epsilon to some power delta and the uniform Gaussian tail. So MT here is a Gaussian process. So we are comparing U with a Gaussian process. We need this density estimate for T less than some deterministic time, but depending on epsilon. So this estimate is a key ingredient, and somehow we ended up using Mulligan calculus to do this. And that's not the end of the story, because the exit time actually scales like T1 epsilon, which is another deterministic time, but this time can be much larger than T0. So we need to do an iteration to recover the full result. Okay, so this is the first step. We just do computation in the most simple case, but already not too easy. So the second part is we want to extend to a general domain. There's a standard theorem called like Hartmann-Grobman theorem, which gives you a conjugacy between linear and general flows. That is, if we look at this like general picture here, then in a small neighborhood near the origin, you can find a local diffeomorphism under which the flow can be transformed into linear ones. So basically, we can study from step one. We know everything about exits for domains whose image under the diffeomorphism is a cube, a box. Therefore, we know like everything about the set looking like this. It's like a slightly skewed box. So for general domain, we try to find we try to just make a box small enough so that it's contained in the general domain. And then we try to use Bradley and Wenzel large deviation estimates to relate the exit events happening on the general domain to that's happening on the like skewed box type set. Basically, we are saying once the process exits the kind of skewed box domain, it's going to follow the deterministic flow up to a very small error, and we claim that error is controllable. It doesn't. It kind of preserves all the estimates. Okay, so yeah, so this is step two, and yeah, I think that's it for my talk. I Yeah, I hope I explained this clearly. Thanks.